Hello. This video and the one accompanying it prove to you why Gaussian elimination works, okay? Why it is that if you have a system of equations, which is equivalent to a matrix equation AX equal to B, if that has some solution set S, in other words, it's a set of all of these x's that satisfy that equation. If it has a solution set S, while another equation, A prime x equal to B prime, has solution set S prime, and where it's true that the augmented matrix AB is row equivalent to A prime, B prime, then the solution set of the first is exactly the same as the solution set of the row equivalent augmented matrix. Okay, so this once we prove this, you will understand a bunch of things. Hopefully, why Gaussian elimination works, why the rref button and rref button are used over and over again. Okay, to be able to prove this, I need 3 lemmas. So this video is going to give you lemma 1 and lemma 2, and the next video is going to give you lemma 3 and putting it all together, proving this big claim in blue. Okay. So lemma 1, and again, this proof is in quotes here. So suppose AX is equal to B, with A an m by n matrix, X an n by 1 matrix, B an n by 1 matrix. Of course, that would result if you multiplied m by n by 1, you get an n by 1 here. Excuse me, that's m by 1. There. Okay, so suppose you have these column matrices and this matrix here such that this equation is true. And I'm assuming we're talking about matrices with all real entries. Okay. Then for any, that's m by m matrix with real entries, it's going to be true that if you multiply on the left of AX, if you multiply by C, that will be equal to the result of multiplying B, which is m by 1, by the C, which is m by m. Okay, so the dimensions are all working. What is the idea here? We are going to assume from your results previous in 13-14 that matrix multiplication satisfies all the usual properties of algebra, in particular this one, the golden rule, that if you have an equation that's true and whatever you do to one side of the equation, you also do the other side of the equation, then you have another equation that is true. Okay, we're going to assume that. All right, lemma 2 says that every elementary row operation, remember Gaussian elimination is just a sequence of elementary row operations. Every elementary row operation on the augmented matrix AB is equivalent to multiplying on the left both sides of, excuse me, that should be the equation AX equal to B here. By an elementary, so multiplying both sides of this equation on the left by an elementary matrix EI. All right. So a couple of things going on in this. I'm talking to you about your elementary row operations, and I'm introducing this idea of a corresponding elementary matrix for each type of row operation. All right, so for example, the row operation of switching rows I and J. If you remember, originally we were talking about systems of equations. If you switched two equations within that system, it's still the same system, right? So switching 2 rows in the augmented matrix doesn't change the system of equations, doesn't change the augmented matrix solution. how can we get the same operation from an elementary matrix? Well, you develop the elementary matrix E, switching I and J, by starting with the identity matrix and switch its two rows, I and J. So for example, you can get E that switches rows 1 and 3 from identity 3 by 3. Here we just switched the first row, which was 1, 0, 0, with the third row, which was 0, 0, 1. So that's our elementary matrix, E1, 3. Try to adjust this camera to get you to see that whole thing. Okay, so taking this, I'm going to demonstrate how we can show that if we multiply the matrix A, which is 1, 2, 3, 4, 5, 6, 7, 8, 9 for simplicity, if we multiply it on the left by this E1, 3 switch, it's going to do the same thing as performing the elementary row operation. Right, so if you had A and you switched rows 1 and 3, you would get 7, 8, 9, 4, 5, 6, 1, 2, 3. Well, notice the same thing happens if I take A, 1, 2, 3, 4, 5, 6, 7, 8, 9, multiply it on the left by 0, 0, 1, 0, 1, 0, 1, 0, 0, right? So, difficulty getting this camera to move down. Dear. Let's undo it. Okay. Which of these guys is going to do this? Sorry about that. So, all right, multiplying on the left. So 0, 0, 1, look what that does when you multiply this on the left of A. It ignores the first two rows and picks up that last row, but puts it in the first row. Multiplying by this, which hasn't been changed, of course, doesn't change anything. As you go through and multiply by this, it just ignores the first and third rows and picks up the second row. So you still get 4, 5, 6. But 1, 0, 0 in the last row here will ignore the last two rows and just pick up the first row, but it put it into the third spot. Third row. Okay. So that's not a proof, but it seems to be fairly effective in getting students to understand what's going on. All right. So now let's look at this second row operation here. Hope you guys can see all that. The second row operation. Yes, multiplying a row I by some scalar alpha not equal to 0. We write that as new row I is equal to old row I times alpha. When you're writing out your row operations, right? I ask you to write it out that way for your sake and mine. So if we perform the same operation on IN, n by n identity matrix, we're going to get an elementary matrix we call E alpha I. And that just looks like the identity matrix with alpha instead of I in the ith row. Okay? So I'm performing the row operation on the identity matrix. It gives me an elementary matrix. And now let me show you an example of using it. For example, if I performed new row 2 is equal to old row 2 times 5 on the identity matrix, I would get this, E5, 2. I guess I should just call that, put a 2 there. E5, 2. Okay, then if I multiply the matrix A, 1, 2, 3, 4, 5, 6, 7, 8, 9, if I multiply it on the left by 1, 0, 0, 0, 5, 0, 0, 0, 1, look what happens. As the first row goes through, it just picks up the first row as usual. When the last row is multiplied through, it just ignores everything. In rows 1 and 2, it just picks up the last row, and you've got the same. But in this middle row, the 0, 5, 0 ignores rows 1 and 3 and multiplies each of those by 5, getting 20, 25, 30. Well, that is exactly the same thing as what would happen to if we performed the row operation. New row 2 equals old row 2 times 5 on the matrix A. Third row operation. And this is the most complicated one, but you will see in a while when we get determinants that this one is the kind of the best one. And that row operation, what elementary matrix does it have? Should be good. Okay. So again, to get the elementary matrix, all you do is perform that operation on the identity, the corresponding identity matrix. What does that look like? So if this was the identity matrix, it would just have zeros everywhere except for ones on the diagonal, right? But the elementary matrix I alpha j, for alpha non-zero and I not equal to j, will produce this, because we took the ith row and multiplied it by alpha and added that to row j. Remember, with this row operation, your new row j has to be equal to its old self without any scalar multiple, to which you are adding a scalar multiple of a different row. That's the only way that is an elementary row operation. So that's what the elementary matrix ei alpha j will look like. In the ith, jth spot, there'll be an alpha. That's the only difference from an identity matrix. An example. Let's say we're performing new row 3 equals old row 3 plus 5 times row 1. Okay. If you perform that on the identity, the 3 by 3 identity matrix, you'll get 1, 0, 0, 0, 1, 0, 5, 0, 1. So it looks just like an identity matrix, but there's a 5 in the in the 3, 1 spot, right? It's a new third row, first column. So if we take that matrix and multiply it on the left by A, you can see this, that matrix there multiplied by this one. So again, going through the multiplication, the first row just picks up that 1, 2, 3, puts it down. Second row, again, ignores everything but the second row, puts it down. Third row, 5, 0, 1, takes that 5 and gets multiplied all the way across 1, 2, 3. And then added to what happens in row 1. With that 1 there, it picks up row 3 and adds it to 5 or alpha times row 1. So if you had 5 times row 1, that would give you 5, 10, 15. And if you added those to the old 7, 8, 9, sure enough, you get 12, 18, 24. Okay? So now you have lemmas 1 and 2. The third lemma I'm going to prove, that's going to get us ready for proving that Gaussian elimination works all the time. And again, this is, I'm using the word proof rather loosely here today in the interest of time. So where we're headed, again, is what's up there in the blue. Here, this is our big claim that we're headed for. In the next video, we're going to prove lemma 3. Every elementary row operation is reversible, can be undone by another elementary row operation, and every elementary matrix therefore has an elementary matrix inverse, EI inverse. Next video.